This is a review of finite state machines. This is primarily CPE 133 knowledge. If you didn't learn it then, now's your chance. So what we're going to review is kind of high-level state machines, and then we're going to move towards modeling those state machines using Verilog. Now, when you talk about modeling state machines, what we're skipping over here is the state diagram. So the state diagram, generating the state diagram, is the engineering step. We're not going to talk about that here. We're going to say, now you have a state diagram, how do you model that state diagram in Verilog? Finite state machines, I know them as circuits that control other circuits. So the idea it's a digital circuit that controls some other digital circuit. They come in two flavors, Mealy versus Moore machines. We will talk about that in a second. But the three main parts here are a next state decoder, and then we have the state registers. This is the actual memory in there. And then we have the output decoders. So the decoders are both combinatorial. State registers are sequential because they do have memory. So this is the top diagram here is a generic finite state machine model, and it's essentially what you saw on the other page, but expanded a little. But these have outputs, and the idea here is a state machine is going to react to the state or the external input. So essentially these outputs here are control signals to other circuits out there. And so we have two types of control outputs here. The Moore outputs, they're a function of the present state only. And then we have Mealy outputs, and they see the Mealy outputs, there's two lines here, right? One line is the present state, the other line is the external input. So we've got two flavors of outputs there. That Moore are only dependent upon the present state, and the Mealy are dependent upon this present state and the external inputs. That's how we know state machines, but we need to model them now. So what we're essentially going to do is divide this into two processes. One is going to be all the combinatorial stuff, and the other one is going to be all the sequential stuff. So the sequential stuff is the state registers. The combinatorial stuff is these two decoders, which I effectively combined the next state decoder and the output decoder. And so the inputs, external inputs that are kind of synchronous in nature are going to be fed into the combinatorial process, and we'll have some asynchronous inputs that we oftentimes don't use that, but those are going to be fed into the sequential process. So let's look at an implementation of this. And so I guess some background information here. Many ways to model state machines in Verilog. I know one way. I'm pretty good at it because I've used it so much. You show me a different way, it's going to be valid. I'm not going to be very good at it. I'm not very experienced with that. So I pick one way, stick to it. I never have to learn anything else. Okay, once again, the engineering step is coming up with a state diagram. This is pretty much grunt work, translating that state diagram into a Verilog model. And I don't do this every time. I have a template out there, and it shows me everything I need to know, and what we're going to do is step through that template. Don't try to write this from scratch. You'll make mistakes. But you got to know the template. You got to know how the template works. So this is my code here. It's just a top level code. It has a clock. It has an external input, which we call X in, and then it has a reset input. And you're going to see that the reset is going to be asynchronous. Okay, it has two outputs in here. I call them Mealy and Moore. As you could guess, one of these is going to be flavored as a Mealy type output. The other one is going to be flavored as a Moore type output. And the important thing is that you realize exactly what makes them a Mealy and a Moore output in the code itself. But this is, I call this the interface, okay? So that's what, it's just the listing of the inputs and outputs. Okay, so this is my state diagram. I just made it up. I tried to put a little bit of everything in there, and we'll talking about that in a second. But important things in here is how to represent this thing. And so there's First thing you see up there is the state bubbles. So how do you represent the states? This is how I do it. I got this line here where I declare two types of register variables, and then down in this line right here, I define my states. Okay, so if you're using System Verilog, this is a little bit different, but for us I'm using this parameter here, and I'm going to define those state variables directly. Okay, so the state A is going to be defined as 0, 0 state. State B is the 0, 1 state. State C is the 1, 1 state. Okay, completely arbitrary, but it works. Notice both these lines here are defined 2 bits. Okay, so those are my states. I'm going to actually give them better names than state A and state B in my code. I'm going to make them self-commenting, but this is just a brief example. This is the state register model. Okay, so I know it's a state register model simply because it has a neg edge or a pos edge in the sensitivity list of the always block. And once I do that, everything that's assigned in this always block is a register, and the thing I'm assigning in this always block is PS. So PS represents the state registers, which is good because that's how I defined them. So NS, it's sitting there, but it is not going to be a register. PS is the register simply because PS is the only thing being assigned in this state. Now, one of the things you see here is you see a neg edge reset and a pos edge clock. And so what this neg edge reset is, I threw that in there because that's how I represent an asynchronous input. So here's my asynchronous input right there, right? Okay, it's an arrow coming in out of nowhere, meaning it's not synchronized to, we'll say, the system clock up here. All the other transitions go from state to state. They are synchronized with the clock. This is done a little bit differently, and you can see it in the model there. And the idea here is if the pos edge kicked off this always block, that means that this line right here would be ignored, and this one would be evaluated. If the neg edge set off the always block, this reset n would be a 0. And this is what would be evaluated. Okay, so they work really nicely together on these things. Important thing is you understand that one's synchronous, the other one's asynchronous. These are, this is implementing the states. Now this here is that I have 3 states, and I'm going to implement this as a more. I'm going to implement this using a case statement, and there's going to be one state clause for each state. So there's 1, 2, and 3, and it does have a default. I need a default in it because I have 2 state variables and I only have 3 states. There's 1 extra state, so I need to put a default in there. First thing I see in here is this always block is sensitive to the present state, which you know was changing in the state registers, which is in this state right here. Present state is being changed, but when present state gets tweaked, it fires off this process. The first thing I do in this process is in this line right here. I take every output and it looks like I assign it a value, but what's really happening is it's not being assigned a value, it's being, these values are scheduled to be assigned. Okay, so what I'm going to do is take every single output in my state machine, and these are all considered control outputs. I'm going to assign everything a value. And if I do that, that means this piece of code here, this always block, will never generate a latch. If it generates a latch, I'm in trouble. It just operates stupid, and it's hard to fix. So I'm doing everything I can to avoid a latch. Now the thing you could do instead is, I'm not sure if I do it or not, but it looks like I do it, so not a big deal. But in every state, I assign mealy and more value, and it looks like I do in this state machine, so not a big deal. But I still, out of habit, take every single output and assign it a value up in this line right here. So this, for example, this is assigned a 0, but here I assign it a 1, right? Perfectly valid. because I didn't really do assignment. I scheduled them to be assigned, and if I come down here, I reschedule it, that's fine. It just, when this always block terminates, everything that has been scheduled is going to be written, and so it doesn't really care if it's been rescheduled or not. So the first thing to notice in this is the more outputs. The more outputs are only a function of state. So there's a more right there. State A, it's implementing this thing. The more in state B has a bar over it, and that's why I assigned it 0 here. State C has the more assigned as 1 here. And the exciting thing is these mores are in the state clause, but it is not in the conditional. So the conditionals here handle two things. It handles where it's going to transition to, and the outputs are always also a function of the input. And so what we have here is here's the input. It determines the state transition right here. But here's the Mealy output. I put it right next to the input right there, simply because there's nowhere else to put it. And so this is the slash notation is inputs on the left, outputs on the right. It's the input that decides how this is going to transition. The outputs are associated with the input. The output is not in any way associated with the transition. Okay, so you can see it. So look at over here. If X is a 1, it goes back to state A, and immediately is a 0. If X is a 1, it goes back to state A. Next state is assigned in A, and immediately is a 0. Or else, immediately is a 1, and it goes to state B. Okay, there it is. Immediately is a 1. It goes to state B when X in is not 1, which means it's 0. Okay, so this state here, the state B, there's nothing conditional about it. It unconditionally transfers from state B to state C. And state C, it's the same stuff all over again. Very similar to state A. The conditional handles where it's going to transition to. It also handles the outputs, because the outputs are also based upon the inputs. The inputs being X1 in this case. Okay, so the important thing is you know how this operates. I am going to ask you questions about it in the lab final. You got to know this stuff. So in the end, what I have here is these bunch of blocks, combinatorial blocks, computer peripherals, sequential blocks. They're all under the control of something. And for us in this class, it's going to be a state machine. For you in a later class, it's going to be a microcontroller. And I think that's it. I hope this helps. Ask me questions if it doesn't.